Okay, welcome everybody. How are you doing?
Good.
Good?
Amazing.
Amazing. Wow. All right. What is amazing?
It's September 21st.
Thursday? What? Class? Oh, that's so kind of you. Yeah, we're gonna have fun. So administratively, I still need to send up signups for the labs. I'm hoping to get that done tonight or tomorrow. What does that mean? Saturday or Monday. No, well, hopefully we'll be able to get things going. Okay, so that we have people there Tuesday night or during this time next Tuesday. All right. So once again, once you look at it, look at who you want to be with and agree on signing up. There was a question about let's see. The syllabus. And I realize I still haven't put it up. On the website. All right, so thank you for your patience. Wait a second. This is not the right class. Oh, come on. All right, so here we go. So at this point, we have today 9:21, session 6, and we have a long ways to go until we get to the 12th. And there are a couple of things here. One, I understand there may be an exam that some of you have immediately before this class on that evening. Okay. We need to figure out something. So I would just talk to the other professor, and we both said, well, we picked that date to not conflict with the holidays. So we need to go and see if we can find another. We'll try to figure something out. More relevant to the content, there was a question of what is covered on this exam. All right. So if we move this exam up or down, what will happen is the content for which we will be covering on the exam will be the penultimate session. Okay, so for example, session 11 will not be on the exam, but session 10 would be on the exam. Okay, does that make sense? And I actually kind of liked it there because we would get through torsion and then we wouldn't have to focus too much on beams, okay? But if we end up moving to later, to the 17th, then what we might do is just say, okay, it's not the penultimate, but don't worry, the last couple, all right, are not there. Any questions or concerns on that? All right, thank you. Okay, let's get going on the technical content. So, today we are on material properties. Again, okay? And what were the primary material properties that we covered last time? Elasticity, okay, so we covered last time. We covered elastic modulus, right? E, and we also focused quite a bit on the, what else? Strength, right? And we denote these with those symbols. Okay? Today we're going to continue building on elasticity and plasticity. Okay? In other words, plasticity is when it goes and deforms and doesn't go back to its original shape. And we're going to introduce a couple of models. We have the linearly elastic, perfectly plastic model. Okay? What does that look like? For those of you who have already been looking at the notes, all right, what do we have? You guys tell me, what do I draw here on the x and y axes? What do I have? Okay, great. So before I even do that, that's exactly right. So we'll go ahead and draw what you just said. Okay, that's the linear elastic, perfectly plastic. And what do I draw on the y-axis? Well, yeah, so y-axis first?
Stress.
Yes, okay, so we have stress. And what are your favorite units of stress now? Yeah, I would say megapascals should be your favorite units of stress at this point, okay? So usually this is going to be in megapascals. And mega means 10 to the 6, all right? And then here we often write strain. And what are your favorite units? Huh? There are no units. So usually you say my favorite, yeah, it's like none, right? Or what are the perplexing units that make us get confused? Percentage, usually, right? That's when you divide, you're like, Fred, it's not 0.1%, it's 0.1%, right, is 0.001. All right, so that we often say it's unitless or it's in percent, right? Okay, so which is the perfectly plastic portion of this? The straight part, right? They're both straight. Haha. No, the horizontal portion, right? Okay, so this is what happens at the yield, all right, SY, and then we have this behavior here. Now, we talked last time about how if you go up this curve, right, we load and then we keep going up, right, and we come around, okay, and then we stop there, we're going to come back down like this, okay, and then we'll have some residual strain. Okay, why is that residual strain and not residual stress in this case? Because it turns out when you get into, and DMC will cover this, when you get into more complex geometries, like beam bending, you can have portions, because of this material behavior, you have portions that actually end up with residual compression and residual tension, okay? But for now, what we're saying is there's no residual stress if I unload completely, but we do have residual strain, right? Because we've moved on the x-axis. And then the other model that you all, or we all have the opportunity to think about, right, is, someone shout it out, please. Or raise your hand and we'll call. What's the other model? Yes.
Linearly plastic.
Yes, right. So linearly plastic. right? So in this model, I go up, and the slope then becomes less, right? And this is still happening around the yield strength, around there, okay? And we know that this regime, this part, right, if I draw E and 1, it's not super practical to write it like that, okay? Or it's practical to write it like that so I can have it. But it's not, to get to 100% strain, you'd be off the mark, okay, for most materials. So what you have here is some lesser, okay, slope here that we can define, all right? And what's interesting here, as we talked about in the last meeting we had, that if you go up, right? And you come back down to have 0 residual stress, but a bunch of residual strain, you can go up and now you're up at a higher yield strain. Okay, it's a new yield strain. And in this model, that's why we call it strain hardening. In this model, you come back, but your yield doesn't go up, right? You go back up this curve or this line, and you just end up at the same location. Now, you'll see that in addition, right, to this property, or to these new graphs, all right, and this, you can calculate what this like new, SY new might be, we also now get concerned about what the area is under these curves, okay? And we introduce two relations for that. Okay, we introduce modulus of resilience and modulus of toughness. So modulus of resilience right? There's got to be some song about, or pop song about you getting knocked down and you getting up again, right? You're resilient if you're able to do that, okay? So this means that what happens is that, we're only concerned with what happens in the elastic portion, okay? That's modulus of resilience. Now, the curve can do whatever it wants afterward, right? But this is the area for modulus of resilience. Okay? So we might call that MR or something like that, right? Whatever this energy is, this is what we can recover. Okay, we can go up and down this. All right. Now, what are the units of modulus of resilience?
Pascal.
Yes. Why are they pascals?
Because the epsilon doesn't have.
Right. That's absolutely right, Daniel. So it's an area, right? But we said this is dimensionless, and this has pascals, right? And so we're going to do 1/2, base times height to get our area, and it's going to end up having units of pascals or sometimes kilopascals, because it tends to be small. Okay, so this is going to be units of okay, and the modulus of toughness, right, is kind of a metric of how much energy can the material absorb before it, ooh, these are fun Halloween colors, all right, before it breaks completely, okay? So in this case, we're concerned about all the area under the curve. Okay? And in this case, there are a couple ways to calculate this area, right? One is, okay, modulus of resilience, and then I figured out what this additional area is. Okay, like when I say additional area, what do I mean? I mean like this, right? So I could say that MR, and if I say this is, let's just call this, well, we'll call it epsilon y, that's what it is. We'll call this epsilon f, that's what it is. Okay, this is sigma y, and this is sigma f at the back, all right? So MR, you can think of, okay, it's going to be this region, right, which we already calculated as the MT, okay, this is going to be MR, now plus. What are some easy ways, or maybe not easy, but what are some ways to calculate out this area? Yes? Okay, so you could look at it as the top is a triangle, and then you have this rectangle underneath. Yeah, that's one way. That's a good way to do it. All right. So we can say, okay, upper triangle. Let me say this. We'll call this the upper triangle. Okay, and we call this the clastic rectangle. Right. So we could say area of upper plus area of plastic rectangle. Okay, that's fine. What's another way you can do it? How else? How else can we calculate that area? Yeah? Okay, take an integral. Woo-hoo. Yeah, that's a good way that you could do that. All right. Yes. Right. So you can come up with an expression. Right. This would be essentially saying, okay, we have at this, figure out what this is, figure out what the y-intercept is, come up with an expression, and then integrate from epsilon y to epsilon f with respect to epsilon. Yes, you could do that, and that's what area is. What's another way? Think geometry. Huh? I heard it. Yeah, it's a trapezoid, all right? It's a trapezoid here. If you think about it, right, from here to here to here, that's a trapezoid, okay? So what is the formula for the area of a trapezoid? Well, it's going to be the average of this one and this one times this is height. Okay, so it's actually something that looks a little bit funny, but it's the average of, we'll say, sigma y, okay, plus sigma f, okay? So so we're figuring out what the average length, I mean, maybe I should, I don't know if I want to tip it this way, but it's probably helpful. Okay, so if I say this is the top, and it looks like this, and this is this, and this is this. Okay, so this was sigma f right here. This was sigma y right here. Okay, in terms of, and we'll call this like a 0 and a 0 here, right? So those are the horizontal lengths. And then we need to know the height. So this height is epsilon f minus epsilon y. Okay. Either way, all right. And I'll give props to the guy who said integral, the person who said integral. Okay. So you could also take the integral. Oops. Now, there's one more. So there are lots of, you're like, wait, what happened? You were just like introducing one concept at a time. Now we've got like 4 concepts, all right? And we're going to introduce a 5th, okay? And what is that 5th concept? You've been very, very participative. You don't know this one. Okay, what's the 5th principle in this session? Any ideas? What's in this session that we haven't covered? I mean, you could look right now. It's fine. I'm not going to know, and I just want to get in. Yeah. What's the next thing that we haven't talked about yet? I'm kind of eager to hear how someone pronounces it, actually. Oh, you even pronounced it correctly. All right, Poisson ratio. I think you pronounced it correctly. I'm not French, but I don't speak French, I should say. Yeah, but yes, the last concept is okay. All right, so what is this? We'll give someone else a shot. All right, give someone else a shot. Anyone? I know you were done with like session 6 last time. So what's the Poisson's ratio? Yeah, if you know.
It's the ratio of of strain and I forget it's like strain lateral.
Yeah, that's excellent. That's excellent. Okay, so it is, and I had to make sure I got it right too. Okay, so the Poisson's ratio is given by, anyone know what that Greek letter is that we're going to add to our repertoire? Yes. Whoops. Not. Okay. So what in the world did we just write? We just wrote an equation, okay? And in words, not equation speak, what is this? I like you said ratio, right? This is a ratio, okay? So we could say it's a ratio, and it already is, right? Okay, ratio. What? Someone's saying something. What? Yes?
Is it the ratio of the shear strain and the axial strain?
So this is no shear yet. No shear, okay, no shear. But it's a ratio of, what did you say?
Strain.
Strains, yes, okay. All right. And what is longitudinal? Long, you're like, yes, all right, okay. And what do you think latitudinal would be? Up and down, or maybe across, up and down, right? Okay. So if I pull on a material this way, what happens to the strain? Well, we say that would be a positive strain longitudinally speaking, right? So if I've got, a little bar, right, and I'm pulling on it, right, I know how to calculate a nice little, whoops, longitudinal strain, right? So there's, and we could even say that there's some stress or some force, right, being, right, and of course there's an internal force and an internal stress in the member, right? And so this is straining, right? The strain, okay, maybe I better go back and say what this is, right? So if I have some, right, if we have some initial length, right, this longitudinal is, how much did that initial length, or it's the ratio of, that's a ratio in itself, right? It's the change in length divided by the initial length, okay? And they're typically very small. Okay, so then what is the Poisson ratio? The Poisson ratio is going to tell us something about what's happening laterally. So if you stretch me out, okay, and actually I made a mistake when I explained this the first time, okay? Anyone watch The Princess Bride? Okay, this is not the machine. The Princess Bride in that movie, they have something that sucks your life out. I thought it was like a rack where they stretch you out, but I was mistaken. Okay, it's not. Okay, and then they like pronounce the guy. Actually, I don't remember. I need to watch the movie again, right? But like, in the end, they're like the guy is like half dead or only what something. Anyone help me out here? Princess Bride.
And gets the bride.
He gets.
And after
Yeah, okay. All right. Yes.
bunch of yeah, they stopped a bunch of skiers.
Yes. Okay, good. Right. So the in this case we don't think of that movie, I guess, but the idea is that we're elongating something. So what happens if you were to put me in a stretching machine, right? What would happen to my cross-sectional area? It would go down, right? It's going to shrink, okay? And that's where this negative comes in, okay? The negative is meaning that it's not growing, it's actually decreasing, okay? So a positive Poisson ratio is what you expect for a normal material. Where you stretch it in one direction, what is normal? The metals that we're dealing with, okay, these solid materials. And it's contracting, right? It's going to contract some amount laterally. Okay, so if I look at the change in the diameter over d, the original diameter, right? This is what we have for this lateral, and I can say that it's going to be nu times epsilon, whoops, with a negative sign, okay? So it's a negative strain, it's shrinking. Now, there are examples of what we call metamaterials. Some of them might be things that involve folding or origami, where when you stretch in one direction, okay, it actually can cause it to expand. Okay, and this top class of materials is called auxetic materials as well. Okay, so they have a negative Poisson ratio. Don't worry about that. Okay, we're dealing with materials in this class that have positive Poisson ratios. Okay, all right. So there's some additional math, okay, that you can go through. All right. Nonetheless, we can also think about this expression. Okay, so what have we written here? Hooke's law, right? This is Hooke's law, and it's what we've been getting very comfortable with, right? We say, hey, sigma is equal to E epsilon. True, if it's uniaxial loading, okay? But what happens if I pull, so now instead you guys decided you're gonna pull me this way, right? But this was my longitudinal direction, and so now you like pull me this way, and you pull me this way. You pull me these two directions. You're gonna cause me to get even shorter than I already am, okay? So that is something that we actually can account for, all right? And the way we do that is through the Poisson ratio. Okay? And this is true in 3 dimensions. Okay? So in math, that describes this behavior. If So, if there is no stress in these opposite directions, or I should say opposite, in these orthogonal directions, okay? So like if I'm just, putting me in a tensile testing machine and I'm stretching me, right? Then yes, I just can say epsilon, my strain in the x direction, if that's x, is going to be related through the elastic modulus and the stress, okay? But if at the same time you try to pull me in this direction and in this direction, then I'm going to actually reduce my height and they're going to compete against each other, okay? And then this happens in a y direction, it can happen in a z direction, all right? Where the stresses in orthogonal directions, so y and z are orthogonal to x and z are orthogonal to y, x and y are orthogonal to z, right? This accounts, this material property accounts for this interesting strain due to stresses in orthogonal directions. Any questions on this? Any questions? Yes.
Will there ever be a case where we have to, let's say, magnitude strands, we have to bring it down to each direction strand?
Yeah, I mean, there are going to be cases where, yes, we need to, yeah, we're going to need to be able to think about, okay, I've got combined loading, all right, is what we end up calling it, and I've got stresses, normal stresses in a couple of directions, okay, and I'm interested in a strain, right, and I've got to account for what's happening in the orthogonal direction. One example where this can happen is in pressure vessels, in cylindrical pressure vessels. Okay, for example, you're going to have stress in two axes orthogonal to each other. Okay, and so that could affect the strain. They can affect each other's strain. Okay. All right. Any other questions, thoughts, concerns, hopes? Okay. Some of you are thinking this is super cool. You really are. And some of you are thinking, I hate this. All right. And some of us are just like, what's going on? All right. Let's try to accommodate everyone's feelings, all right, and emotions toward the problems as we go forward. All right. And with that, we reach the moment you've been waiting for. All right. Is it not up? Oh. Okay, hold on. That will make things kind of interesting, won't it?
Like, I know this is scary, I guess it's scary. It's just the straight of the latitude. Just whatever you know, whatever you don't know, is your
Yes. Yes, working on it.
that's different. Yes.
Thank you. I made a mistake.
The initial work on it? Yeah. Yeah, I got stuff on 4, 5, 6 is all this thing from us.
If you don't know by then, I got your,
Symmetrically the same. So, so in the notes that in you can actually calculate changes from X, Y, and Z, but once you actually begin to because you know each group has we just said this was
Okay, we should be good. Sure, what's up?
so I was actually
Yeah.
kind of interested in getting back to myself.
Okay.
and so does that mean that I tried to
Website,
So if you're on campus, it should come up because that's the polymer processing and engineering. That's a long time ago. But yeah, that one, yeah, you can, if you are on campus, or if you're not on campus, I'm on campus. Okay, if you're on campus, then it should come up. If it doesn't, I can get you a copy.
thank you. I just Thank you.
Yes. Yes.
Well, I didn't get it right, but I also have another question. So
Yes.
this is my formula for work.
Or for the weight.
Yeah.
Okay, so we have the volume. So
It
I
says
was,
that L might be a W.
so this is rho, L, H, T, yeah, sure, times D, okay, I agree.
But my question is, I'm assuming units just to like triple check everything.
Yes,
So rho is kilogram per meter cubed,
correct,
and then meter, and gravity.
yes.
So that would be
9.81, yeah.
units. But is it work is in meters? So I'm missing meter.
No, this is weight.
Oh.
This is not work, this is weight. Okay, so weight is what we need because we need a force to get to. Yeah, good. I'm glad you asked.
So
Yeah.
I kind of like, I try to run time, I try to, I broke it down like into like, just two sections, and then like these spring constants like double to the original.
Why the?
I don't know, I try to like it one time, I don't know where to start, but okay, that's what I tried, and I ended up back in the equation. It didn't work.
No.
I guess I'm just looking for a place to start.
Okay, why don't we? That problem is probably going to trip it's going to be a little tricky. Okay, so there are multiple ways to solve it. Let's see. Is that the last one?
Yeah.
Okay. Yeah. All right. So let me do this. All right. If you're interested, we're going to look at, is that Q8?
Yeah.
Q8. All right. So I will jump to the answer, and then I will show you how I'm not quite sure if this answer is the way, I think it's the way I like it. But if you look at the exam 1 from the spring, okay. Okay, this is what I wrote. So there's the answer. But let's talk about how you do it. Okay? So there are a couple ways to look at this. All right. You have, this is session 6, right? Okay. All right. So the simple, tricky way to do it, okay, is to think about these two members. Did I say they have K1 and K2? Oh, okay, they have different lengths, right? So they're going to have different K1s, or if they had the same, they would be. So let's say we have a K1 here and a K2 here. All right. So like if I took these apart, that's what we're talking about, right? We're saying that they would have right, and we're saying that this one over here, I'm going to use this color here. Okay, and you're like, okay, that's not that interesting, right? I can say K1 is equal to EA1 over L1. I can say K2 is equal to EA2 over L2. And for our intents and purposes, they have the same cross length, right? So for this problem, A1 is equal to A2. Okay? You're like, boring, right? Still boring. So let's make this a network of springs. All right? And which way did I draw the force? We drew the force this way, right? With it coming down, I think, force, right? So we have displacement and force. And we're interested in what is the effective spring constant, right? There. So what we want is a K effective, which is what? And right? Just for now. I mean that's like if I have this, that's what I'm looking for, right? Okay. So if I draw this out, oh, it's like too smart. Right? I can say, okay, we have a K1 up here, K2 up here, and there's a force being applied here, and we have a delta in that direction too. Okay? We agree? You're like, okay, just rewritten the problem like 3 times. When I pull down here, and if I say it's detached, if I use superposition here, right? The displacement that I get, okay, is going to be right? Okay, and if I, right, pull down here, okay, like this, right? And I define displacement here, right? Then I can say that delta 2 is equal to F over K2. Okay? What has to be true? These displacements, they need to be the same, right? It turns out that I've defined these deltas to be in the same direction, okay? And it turns out that they're both working, the springs are both working against the direction of the force, okay? All right, they're both working in the direction. Now, normally, right, when you have, if this weren't here, okay, then we just say it's like, oh, all I care about is what's happening up here, right? This would be along for the ride. K2, the K2 spring would just be along for the ride, okay? But it's not, right? It's actually contributing. It's actually contributing force, right? And the displacements are the same. This can be rewritten as
You missed something in your calculation.
huh?
It doesn't seem too obvious.
That doesn't seem too obvious, right? What are we saying? We're saying that both the springs are resisting the force that's being applied in the middle. Both have the same displacement, right? We said, right, because they're connected there, right? We have delta 1, we have delta 2, but these displacements have to be the same, all right? So when we write, so now this is the delta that we have overall. This is the same as this delta here, okay? Right? And so here, what is the K effective? The K effective is the sum. That's it. All right.
But if the delta is the same, and if the force is the same,
The force is not necessary. Well, okay. The force is not necessary. It's not the same necessarily. No, you can have. That's the interesting thing here. The forces add up. If I look at these forces add up to this force. Okay. So I can say I have some F1. I should be more careful here, right? I have F1 and F2, right? These forces, F1 plus F2, are going to be equal to the big F. All right? All right? And then what we have here is that, and this is going to be F1, this is F2. Yes. Okay, like that. So when these forces add up, okay, they equal F and the displacements are the same. All right, so I can get to it either way. Okay, so once I know K effective, it's just these two things added to each other.
how do I link this back to
The material properties,
modules?
right, way up here.
I'm having trouble with this
All
one.
right. Okay.
So,
Is that helpful? I hope it's helpful. All
see
right.
one like
Yes.
this. Then you multiply by the density, you get the mass. Multiply by 5.8 for gravity.
And then you wait a couple days and it's
Then you
updated.
divide it by, would it be this cross-sectional area?
Okay, send me a message. I'll take a look at yours.
Okay, perfect.
Yeah, in Canvas, send me a message.
It can be like an email or like
So if you go to the inbox, and you send me a message. Yeah.
to David.
Yeah.
I just wanted to ask about the Poisson's ratio question from today's
Sure.
session 6.
Sure. So this is number
6.
6.
I'm not sure what the best way to go with this is.
Okay.
So the questions here. So the way I tried to approach it was that we know that elastic modulus is strain over stress over strain and longitudinal, right?
Okay, so yes.
And we also know that Poisson's ratio equals negative E lateral over E longitudinal.
Okay.
So since we know the force, we can calculate stress. So we can calculate over a couple steps. We can calculate the lateral strain. And so using this, I thought maybe we can calculate the change in diameter by multiplying the change in lateral strain times diameter converted to meters.
Okay. So with this, right? Have you calculated out what the longitudinal strain is yet?
Yes.
Okay, so you have the number, longitudinal. Okay, so I don't know if that's right, but let's say that's right. Okay, and so then you can calculate out the lateral. There needs to be a negative sign.
Will it only take a negative sign?
Well, there needs to be, here at least, there needs to be negative sign.
Well, because mathematically.
Right,
Okay.
right, because that's what the Poisson ratio is. So yes, there needs to be a negative sign there, right? Okay, and then when you go about it, then you can multiply by the diameter, right? And that should give you the amount of change in diameter.
Okay, so maybe that's what I was missing.
Yeah, do we agree on that? Sorry.
No, I follow. Thank you.
We can go over here.
In the units of micrometers. Listen, strain, what's it like? Strain is unit. And the time. Any microsites. Well, it's just
Micro is what, 10 to the negative 6?
You know, like when you're dividing.
Listen, I don't want to tell you. That's also us.
You're doing 5 right now? So microstrain. Yeah, no, 5. So like, what are you putting in as your answer?
I'm putting in, well, I didn't get it right. But I was going to take the modulus, put it into right, what's called units, divided by the stress, and then get the strain, and then divide that strain, whatever you got, right, by 10 to the negative 6. I got it wrong.
So yeah,
I had some big numbers.
I had just 2 digit numbers. Okay, I got it.
What's your number?
So I got a really small number and then I multiplied by 10 to the 6 to get it to micro. I converted the normal stress into gigapascals and then divided it with the modulus.
Okay, yeah, that's fine.
What's the fucking
I got the last one too, so let me know if you need some help. So I got a quick question about the.
Is it Justin?
No,
No, James. Okay.
No, you got it. So just a quick question about the units for strain.
Yes.
In my statics class, which was at a different institution, we had millimeters per meter.
That's fine.
Okay, so.
But that would be that'd be millistrain.
Sorry, micrometers per meter.
That's fine.
Okay, so
that's gonna be micrometers.
Yeah. Okay. So when we write it out, are you gonna specify if you want it as a percentage or?
Yeah, I am, aren't I?
No, for these, we're not this one, but in the last session, they just put like strain or something.
Oh yeah, if it's a strain, then
The length part of the strain, obviously, that's gonna be in the micrometers. Or like the displacement. When they ask for the displacement.
when I answer this, so if I didn't put it in correctly, I try. But I do make mistakes.
Okay,
So if there's a question where I didn't do it right, let me see. Let me pull up. Is this from session 5?
No, so in session 5, it was just microstrain, which was a terminology I wasn't familiar with.
Okay.
But, hold on, let me see. I don't remember what it was for the displacement. You asked for
It's gonna be
how much
I was saying that to multiply into the end. Like what do you get here?
Okay, no, my bad. No, you did mention micrometers here. Okay.
No, if there anything comes up, just put it on the inbox.
Sure. Yeah, thank you.
Micrometers are what? 10 to 96.
This class, I want to get ahead. I'm getting so busy.
What's your major?
Aerospace.
Becky.
Okay, it's the same thing. Are you in CAD or no? So
I think next semester.
I'm taking that class right now. If you don't know CAD, it takes a long time.
They don't teach you like from the ground up.
Yeah, you do, but I feel like they also expect you to know how to use CAD a little bit too. Like I knew how to use CAD, but some of the terminology they use, like it just expected you to know. I took like 2 hours doing one of the problems.
So what's it like? Each homework is like you have to submit some drawing.
So at least for the first couple of homeworks, we were given a sketch. You need the sketch on time.
Are they like complex shapes?
No, but the way they do it is they don't give you the measurements for all the parts because have you used CAD software? Okay, so you know when you dimension things, at some point the way the values put in for dimensions, they're gonna force other parts of the sketch to be. So they give you some of the dimensions and not all the dimensions.
Why would they do that?
They want you to put it. They want you to create the sketch in a way where when you put the dimensions in, it'll force the rest of the sketch to rectify. This is a valid reason, but in a real life scenario, when you're doing CAD, you're not going to not have some of the dimensions.
Yeah, you're gonna know everything. What's your name, man?
Jay.
Jay. I.
What's up? You sophomore?
What? Sophomore.
Sophomore?
You too?
Nah, I'm a junior. Yeah.
No, zero.
And that's it.
The last question on that. Okay, so let me just go to the board. Okay.
Yeah. Just.
I'm going to the board. Okay. Since there are multiple people, who is asking about the last question at this point? You are. Okay. We have audience. And where's Lanaya? Oh no, wait, you didn't ask. No, who asked about? You asked about someone else raised. Oh no, you asked about. I don't know where that person went. Who was the person? They left. Okay. So first, okay, so there's a question. Let's do this. I gotta get over it. Okay, is that a little bit better? So first, if you want the answer, you just go to exam from spring 2023, and the problem is right here, okay? But let's talk through it, okay? So that's, yes, no, it's okay, all right? I'm sorry, all right? But let's talk about what's going on, because this is just a bunch of math, right? It doesn't really explain the physics of what is happening. So this is a structure that has a stiffness up here and a stiffness up here, okay? And if I were back in this like simple problem where I split it up, right, it wouldn't be that hard. Okay, we would have just a force and a K1 here, right? And a force and a K2 here. And we're trying to figure out what the effective K is relating these two to each other, right? It also would be pretty simple, right, if I had if I was, then this would just, then the displacement down here or here, right, would only be dependent on K1, right? This would just be along for the ride, okay? So there are a couple ways to think about this, all right? Let's think about it maybe slightly roundabout. If I just have the top system. This top system, I could think of having some F1, okay? And I have some displacement delta 1 in the same direction as the delta that I have here, okay? If I look at the second one, I could say, oh, I'm going to define some F2, and then I have some delta 2 related with it, okay? So the question is, or one of the questions is, how do we relate the force and the displacement, the forces and the displacement to each other when we put them together, okay? So do the forces in these individual springs have to be the same? What do you think? It's confusing, all right? The answer is no, okay? They don't have to be. And how can you think about that? You could think, well, this one is going to be in compression, for example, and this one's going to be in tension, all right? And if this problem actually has 3 forces. There's a reaction force up here, and there's a reaction force down here. Okay? And so if I were to take a slice here and here, then I could figure out what the internal forces are in those springs, and they don't have to be the same. Okay? They don't have to be the same. They could be the same, but they don't have to be the same. Okay? What about the displacements? Do these displacements have to be the same? Yes, they have to be the same, right? If the top one goes down delta 1, the bottom one is going to go down delta 1 as well. Okay? So we can kind of start to write some algebra out that delta 1 has to equal delta 2, okay? And this is maybe a little bit of a leap. All right, the forces, they actually add up, all right? Because if I take the junction, if I just look at the junction in the middle, right? Remember, this is like method of joints. That's a joint there. So I can say that this force, that's the overall force, right? I could say that that force is going to be equal to an F1 going up and an F2 also going up. Okay, it's the sum of them, right? That's how you can get, and I think I'm doing a better job explaining this than I did the last time, whether or not you believe it or not, okay? So use that method of joints and you can figure out this expression, right? Because this is going to be F is equal to F1 plus F2, right? Or I could say, F1 plus F2 minus F is equal to 0. Okay. So, now you can do the algebra, all right, to figure out what you're going to satisfy, all right, with this. Yes. What's that? Oh, sure, I'll do the steps. Okay, so we have F equals F1 plus F2, all right? We have delta 1 equals delta 2, and we have delta 2, or delta 1 is equal to F2 over K2. F1 over K1, thinking too fast, F2 over K2. All right? So what do? Well, we can say that this is F now is going to be equal to K1 delta 1. This is going to be equal to K2 delta 2, right? And delta 1 and delta 2 are equal to each other. And delta 1 and delta 2 are equal to delta, right? So we have F equal to K1 delta 1 plus K2 delta 1. Delta 1 is equal to delta. Okay. K effective. So you go to K1 plus K2. All right? Yes? That's the trick. No. Okay? Because you have a constraint. I agree. That problem that you're thinking of is this. That is two springs in series. Okay? This is actually two springs in parallel. Look, it's K1 plus K2. All right? But why is that? It's because when springs are in parallel with each other, you satisfy these conditions. The forces from the individual springs add up to the overall force, and the displacements of the springs are the same. That's what it means for springs to be in parallel with each other. Okay? Okay?
They look like they're in series.
That's right. All right, so where you define your boundary conditions, and where you define the delta you're interested in, and where you define the force you're interested in, that all affects things. Yes?
That K effective equals force or displacement is great. We are not given force or displacement.
No, but what are you given?
We're given the elastic modulus of the range bar and its cross-sectional area.
Right? This is from our prior work. All right, for a bar, we can figure out what K1 and K2 are with the elastic modulus, cross-sectional area, and its length. Okay? Good question. Good questions on the questions. Yes? Did I not put them in correctly? Which one is this? Is this the last problem? Because, okay, I think I corrected it. If you submit it incorrectly, which you feel badly about, it should come up with centimeters. Those are units of centimeters. If you reload the problem, Praj told me I made this mistake, but the units should be in centimeters.
Can you scroll back up on that notes page?
Sure. And of course, these notes are available now on the website. Yes? Okay, hold on. Let's get there. Okay. Any other? Are we good? All right. Okay, so question 3.
Professor, would you mind if I'll just take a selfie with that one instead for today?
What do you mean?
Just for the attendance.
Okay.
Yeah, okay.
Let's see. Sure. See you there. I don't have in my notes. I don't have question 3. Let me look at what it is. Did I write? Is question 3 in the notes that I posted?
Yeah, it's under 1.
Ah, yeah. Okay, good. Okay. It's before example 6 too. Yeah, okay. Sometimes that's a little bit awkward. Okay, yeah, so someone else asked about this one too, so we'll go through this. Okay. So in this case, what we have okay. And it's something like this, right? Is this the problem? Okay, and we're saying that we're applying a linear strain of, what do you have? What is your value? What is it asking you? Of 0.22%. Okay, so on this graph, where do you end up?
Right after the 0.2.
Yeah, so somewhere over here, right?
Yeah.
Okay. So now, what happens when you relax? What do we say? We leave the, right? We leave the stress to, where we make the stress 0, right? We're going to go down on the line, on a line with the slope of the elastic modulus.
But isn't it like a horizontal line or vertical?
Yes. So it's over here. It's this case. Sorry. It's this case. Sorry. Okay. So what happens? We're gonna what's this slope, right? I can calculate it out if I want to. Okay. But look, it started at 0. And when it's up at the same level, it went over 0.1%. So how far to the left am I going to go? I'm going to go back down. I'm at the same y.
That same x value that you would get from that slope.
Right, so it's 0.1%. Right, so I'm going to go back down 0.1%. Okay, this is not to scale. Yeah, but this amount is going to be 0.1%. Okay, so not to scale. Not to scale. All right, so the residual strain is just going to be the applied minus the 0.1%. And actually a better way to write this, in this case, if it's perfectly placid, is the strain at yield. Okay. So in your case, it's going to be, the residual strain is going to be 0.12%. Okay. So now they want the change in length in micrometers, right? Or I want the change in length in millimeters.
And then would you take on the strain is equal to the change in length over the length?
Okay. And then, so what is the change in length? There you go. Okay? Make sure you convert to millimeters. Okay. It's time to say goodbye. Thank you, everybody.